everyone. I'm Aryan Sumanna and we'll be covering machine learning for data analytics. This is the first unit of a 5-unit course. Let's begin. Okay. What is learning? A computer program is set to learn from experience with respect to some class of tasks T and performance measure. If its performance at that particular task, which is measured by P, it improves with experience. Moving on to machine learning. Machine learning is the branch of AI that enables algorithms to uncover hidden patterns within data sets, which allows them to make predictions on either similar data or new ones without explicit programming for each task. Now, traditionally, machine learning combines data with statistical tools to predict outputs that yields actionable insights. For example, think of email spam filters. Initially, the system is fed labeled examples, that is spam and not spam. Over time, it improves by analyzing patterns like specific keywords or sender behavior. Now, the task T is, if we want a robot to be able to walk, that is, walking is the task, we could program the robot to learn to walk or specify how it should work manually. Now, in order to evaluate a machine learning algorithm, it is classified into 3 different tasks, that is classification, regression and clustering. In this case, we must measure the performance. So for tasks such as classification, we often measure the accuracy of the model, and in this case accuracy is the proportion of examples for which the model produces correct output. Now, experience machine learning algorithms can be broadly classified into 2 different: supervised or unsupervised, based on the experience they are allowed to have. Now, unsupervised learning, it experiences a data set that contains many features, then learns useful properties. Now, in supervised machine learning, it experiences a data set containing features, but each example is also associated with the label or target. Now, machine learning comes under artificial intelligence, and it can be associated with data science as well. Moving on, training versus testing class. Now, training data, it is used to teach the model patterns in the data. For example, predicting house prices and training data will multiplication problems. Results are divided into 4 types. One is true positive. In this, it correctly identifies a positive class. For example, a model correctly predicts a tumor is malignant. Then we have false positive, which is incorrectly identifying a negative class as positive. For example, predicting a benign tumor as malignant. We have true negative, that is the result that we get if we correctly predict the negative class. That is, if a model correctly predicts a tumor is benign. And we also have false positive, that is the outcome that if we get predict a positive class as a negative class. That is, if you miss a malignant tumor in a prediction. The formula for calculating the accuracy is the number of correct predictions divided by the total number of predictions. In other words, TP plus TN divided by true positive plus true negative plus false positive plus false negative. Now we're going to talk about cross-validation. Cross-validation is a statistical model used to evaluate the performance and stability of a machine learning model. It ensures the model generalizes well to unseen data by splitting the dataset into training and validation subsets multiple times. In formal definition, it is a technique to assess how a machine learning model will perform on an independent dataset by training it on a subset of data and testing it on another subset. In machine learning, there is always the need to test the stability. It means based on only on training dataset, that is, we can't fit our model on training dataset. For this purpose, we reserve a particular sample of dataset which is not part of the training dataset. After that, we test our model on that sample before deployment, and this complete process comes under cross-validation. Now, there are three methods of cross-validation, that is reserving some portion of sample dataset, using the rest datasets to train the model, and testing that under the reserved portion of the dataset. Now, there are two types of cross-validations, that is the LOOCV, the K-fold, and the validation set. We will cover more about the validation set right now. Now, in validation set, we divided our input dataset into a training dataset and test or validation set in validation set approach. Both the subsets are given 50% of the dataset. Now, the one big disadvantage is that we are using 50% data to train our model. So it may miss to capture important information which can lead to underfitting model. Now, a random splitting of data set into a certain ratio, the result in. Now, types of cross validation are LOOCV, validation set, and K-fold. We'll be looking into validation set approach. Set approach is basically a simpler technique for evaluating the performance of machine learning models by splitting the dataset into two subsets, one for training and another for validation. Now, in formal definition, the dataset is divided into two parts. One is the training dataset, which is used to train the machine learning model, and the validation set that is used to evaluate the model's performance and determine how well it generalizes to unseen data. The purpose of this model is to assess the model's accuracy before deployment and avoid overfitting to ensure the model works well with underseen data. Now, the steps into validation set approach is it randomly splits the data set into two parts using a specific ratio. Typically, splits are 80% for training and 20% for validation, or it can be 70% for training and 30% for validation as well. The reason why we don't go for 50-50% training approach is because a lot of important features can be missed out, which means the model can be underfitted. The model's accuracy is calculated through the prediction error by using the model's performance matrix. Moving on to LOOCV, it means in this approach only one data point is reserved and the remaining data set is used to train the model. Now, this process repeats for each data point that is there. Hence, for n samples, we get n different training sets and n test set. Moving on to K-fold validation. Now, K-fold cross-validation is basically splitting the data set into K equal sized folds and training on k minus 1 folds and testing on the remaining 1 fold. This process is repeated k times using a different fold on the testing set each time. Now the advantage of K4 cross validation is it reduces bias as all data is used for training and testing, and it provides more robust results compared to a simple train test split. Like for example, take a 5-fold cross validation. It splits the data set into 5 subsets A, B, C, D, E. The iterations are first you train B, C, D, E on and test on A. Then the second will be you train on A, C, D, E and you test on B. Like that, the process continues until you train on A, B, C, D and you test on E, which is the remaining fold. And average the performance matrix across the 5 tests. Is broadly categorized into 4 types: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. We move on to supervised learning. Supervised learning is the most common type of machine learning where the model learns from labeled data. Its working is the dataset contains both input features, that is independent variables, and the corresponding output labels. This model is trained to map inputs to outputs. The 2 tasks in supervised are either classification, that is predict a discrete category or label, and regression, which is predicting a continuous numerical values. For example, we have email spam detection. It is to classify emails as spam or not spam. Or we have a disease diagnosis where we predict a patient has diabetes, and based on that we determine the medicine that is given to the patient. Here in this diagram we have label data and we have labels. They both combined, and which is used to train the model and create a prediction. Now here regression versus classification, both are 2 different types. Now classification, as it is used to basically predict a discrete category, and regression is basically determining regression versus classification. Here classification is basically to assign data points to predefined categories or classes. It is used to predict a discrete value, whereas this regression is used when the output of a variable is continuous and involves predicting a numerical value based on the input features. Now example of regression is predicting the house prices based on the size, location, on number of bedrooms, forecasting stock prices using historical data, or estimating customer lifetime value. Now types of regression are, you can have linear regression, non-linear regression, polynomial regression. Classification on the other hand is used to assign data points to predefined categories or classes. Its key algorithms are logistic regression, decision trees, naive Bayes. As explained, classification, helps to predict a discrete value. It can be thought the input data as a member of a particular group or class. Now examples are naive-Bayes classifier, logistic regression, support vector. And regression, it is used for continuous data. It is used for predicting the price, for example, predicting the price of a piece of land given the area, location, and number of rooms, as explained. Moving on to unsupervised learning. Unsupervised learning, it is a type of machine learning in which the models are trained using unlabeled data set, and in this case the models are allowed to act without any particular supervision. Unsupervised learning explores the structure of the data and identifies a pattern or relationship. Now, this type of learning does not have any predefined labels. The algorithm groups or clusters similar data points based on inherent patterns. Now, in unsupervised learning, we cannot directly apply to regression or classification because unlike supervised learning, we have the input data but there is no proper output data. The goal of unsupervised learning is to find the underlying structure of data set, group the data according to similarities, and represent the data in a compressed format. Here we have the input data. We give it to the model and we process the data based on similarities. Here's the entire process of unsupervised learning. We have the raw input data. We first send it to interpretation where the unknown, which has unknown output and no trained data set. It is sent to the algorithm to learn for model training. The algorithm processes all the data and it classifies the output based on similarities and differences. Now, difference between supervised and unsupervised learning is, in supervised learning, the model is acting under supervision, whereas in unsupervised learning, the model is not acting under supervision. And in both cases, supervised learning is working based on labeled data set, whereas unsupervised learning is based on an unlabeled data set. In supervised learning, the output is already known to the model, whereas in unsupervised learning, the output is not known. Moving on to semi-supervised learning. Semi-supervised learning is a type of machine learning that bridges the gap between supervised and unsupervised learning by using a small amount of labeled data along with a large amount of unlabeled data. So how it works is, the model first learns the patterns from labeled data and then applies these patterns to the unlabeled data for further training. The goal of semi-supervised learning is to learn a function that can accurately predict the output of the variable based on input variables. However, the algorithm is trained on a data set that contains both labeled and unlabeled data. It is useful when there is a large amount of unlabeled data, but it is too expensive or difficult to label all of them. For example, training a language translation system where only a few sentences are labeled with translation while the majority of text is unlabeled. Or in medical imaging where only a few images might be labeled while most images remain unlabeled. The given diagram explains the same, where we have input data and partial labels. Both are combined into a machine learning model along with unlabeled data to make a prediction that the given unlabeled data is an apple. Moving on. Now, overfitting. A model is said to be overfitted when the model does not make an accurate prediction based on testing data. In this case, the model has so much data, it starts to learn from information that makes it inaccurate or the data entries from the data set. While the testing the data, while testing the test data, it results in high variance. The model does not categorize the data correctly because of all these too much details and noise. Basically, overfitting is a problem where the evaluation of machine learning algorithm is different from unseen data. Now, the reasons for overfitting, it can be due to large amount of information. The model may be too complex, and it can also be due to high variance and low bias. A few techniques to reduce overfitting are: we can reduce the complexity of the model, we can reduce the size of the training data, we can also use ridge regularization and lasso regularization. We can improve the quality of training data which reduces overfitting by focusing only on what patterns which are meaningful, thus mitigating the risk of noise and irrelevant features. Underfitting, on the other hand, is basically if the model is way too simple and it does not cover all the important points in a data set. An underfit model is inaccurate when it does not go through unseen examples. It occurs when a model is very simple or it uses overly simplified assumptions. Now, reasons for underfitting are, again, the model is too simple, the size of data set is not enough used for training, all the important features are not scaled properly, and the input features which is used to train the model is not adequate enough. Now, techniques for reducing underfitting are complete opposite for overfitting, which is increasing the complexity of the model, and you remove the noise from the data. You also increase the number of features, performing feature engineering in this. Given the diagrams for overfitting and underfitting, for underfitting we have a straight slope which indicates too simple and explains the variance. For overfitting we have a unique pattern, also known as force fitting, which indicates that the model has too many features. Hence, appropriate fitting, we have a parabola type of graph. Bias refers to the error due to overly simplistic assumptions in the model. It reflects on how well the model captures the true relations in the data. It is error due to the model's inability to represent the true relationship between the input and the output accurately. Now, high bias models are too simple and it fails to capture the complexity of the data. This leads to underfitting, where the model performs poorly on both training and testing data. For example, using a straight line to fit the data that clearly follows a non-linear pattern. Variance, on the other hand, is the error due to the model's sensitivity to fluctuations in the training data. It reflects on how the model's predictions change when the trained data on different subsets of data. Now, the characteristics are high variance models are too complex and it captures the noise as well as the important features, and this leads to overfitting, where the model performs well on training data but poorly on the testing data. Now, for example, we use a high degree polynomial to fit a simple linear relationship, causing the model to memorize the training data altogether. Here the graph indicates both high bias and high variance. For good fitting, we want both a low bias and a low variance. Now, bias variance trade-off, the goal is to find a balance between bias and variance to minimize the total error. Now, the optimal trade-off is the model captures underlying patterns without memorizing the noise. Now, moving on to linear regression. Linear regression is one of the most common ways to perform a predictive analysis. It is used to examine regression estimates, that is to predict the outcome from the set of predictor variables, and which predictor variable have the maximum influence on the outcome variables. This is one of the most simple and easy algorithms which works on regression and shows relationship between the continuous variables. It has two types of linear regression. One is simple linear regression. There is only one input variable, and in multiple linear regression there are more than one input variables. In this case, the relationship between one continuous dependent variable or two more or more dependent variables. Now, the mathematical equation for linear regression is y is equal to ax plus b. In this case, y is the dependent variable, x is the independent variable, and a and b are the linear coefficients for x and y. The dependent variable is called the outcome variable or the criterion variable, and the independent variable is called the exogenous variable. It is also written in the format of b0 plus b1 into x1, or the dependent variable yi is equal to beta naught plus beta 1 plus xi plus ei. Here ei is the random error component, xi is the independent variable, beta 1 is the population slope coefficient, and the linear component comprises of the population y-intercept and the population x-intercept. Moving on to the properties of regression line. The line minimizes the sum of the squared difference between observed values and the predicted values. And secondly, the line passes through the mean of both the independent and dependent features in order to make an accurate prediction. Now, a positive linear regression is with the slope of the graph is positive, whereas in a negative linear regression, the slope of the graph is facing a downwards direction, which indicates the independent variable is. Regularization is a technique used to improve the performance of a machine learning models by reducing overfitting. It does this by adding a penalty term to the loss function, discouraging the model from learning complex patterns that do not generalize well to unseen data. Now, why regularization? When a model performs exceptionally well on a training data but poorly on a testing data, it memorizes noise or irrelevant details. The goal of regularization is to simplify the model by penalizing large coefficients of weights, ensuring it only captures meaningful terms. The role of regularization in machine learning is 1. It prevents overfitting by reducing the model's ability to memorize the training data, and ensures the model focuses on the most important patterns instead of the noise and irrelevant features. Secondly, it improves generalization by helping the model perform well on the unseen test data. by balancing the complexity and simplicity. Regularized models avoid being too complex or too simple. Thirdly, it enhances stability in high dimensional data. It handles data sets with many features, preventing overfitting when there are more features than samples. Example, in test classification, L1 regularization eliminates redundant or irrelevant words. Another thing is regularization adjusts the model complexity to strike a balance. That is, it reduces overfitting that may cause underfitting. And low regularization, it captures more patterns but risks overfitting. In general, regularization is a vital tool in machine learning, ensuring models are robust, interpretable, and capable of making accurate predictions on real-world data. It serves as a safeguard against overfitting, leading to better generalization and performance. Moving on to classification. Classification is a supervised learning technique that is used to identify a category of new observations based on training data. So, in classification, a program learns from the given data set and then observations are made and classification into number of classes or groups. This can be either yes or no. If a disease diagnosis is made, whether the patient has disease or not. In classification algorithm, a discrete output function is mapped to an input variable. Error and noise. Error refers to the difference between the predicted values generated by the model and the actual values from the data set. It represents the inaccuracies in the model's prediction. Based on that, there are three types of errors. One will be bias error, second is variance error, and the third is the irreducible error. Now noise refers to the random irrelevant data points in the data set that do not represent the true underlying patterns. This includes data corruption, and it can also mean that any data that a user system cannot understand and interpret correctly. Noise can lead to overfitting as a model tries to fit the noise instead of the actual signal. That in this case, a data is equal to the true signal plus a noise. Noise is often caused due to data collection errors, inconsistent labeling, and random fluctuations in the real world data. And thus, it can increase the amount of storage space required and can adversely affect any data mining analysis results. Metric models are the statistical models that rely on specific assumptions about underlying distribution of population being studied and summarizes the data using a fixed number of parameters. Now, key characteristics of parametric models are it assumes a specific functional form for underlying distribution or relationship between variables. It can have fixed number of parameters, hence the model will have a fixed complexity, and the model learns the parameters based on the training data, and once learned, the model is set. Now, the parameters used for normal distribution are mean and standard deviation, and eventually the classification of a method to be parametric, it completely depends upon the presumptions that are made about a population. Now, different statistical tests under parametric models are your t-test, that is used to differentiate between means of two independent groups, ANOVA it tests for the difference between three or more groups. F test, it compares the variance. Chi-square test, it tests for the relationship between two categorical variables. And correlation analysis, it measures the strength and direction of relationship between two continuous variables. And the different machine learning models are linear regression, logistic regression, naive Bayes, and hidden Markov models. Moving on to non-parametric models. Non-parametric models do not assume specific form or distribution for the data. In this case, they try to model the data more flexible without restricting it to a fixed data set of parameters. Unlike parametric models, non-parametric models make fewer assumptions about the underlying data distribution, and they are more flexible and can adapt to the data. Hence, the complexity of the model can grow to the size of the data, which means more data means more complexity, and these models typically store data and learn from the entire data set during the prediction. Few statistical tests under non-parametric models are the Mann-Whitney U-test, the Kruskal-Wallis test, and the Wilcoxon-Sain-Rank test. And few machine learning models under it are the k-nearest neighbors, where a simple model where the prediction is based on the majority class of the nearest neighbors in the feature space. Decision tree, where the trees split the data based on features valued without assuming any prior distribution. And random forest, where an ensemble of decision trees each trained on a random subset of data. In this case, no assumptions about the data are made. Thank you, everyone.